So in the previous lecture we discussed about the source free response. Now we will talk about the step response. That means the voltage or the excitation whatever is given, it will be a step input. What is the step input? The step input is a DC value, but it starts from t is equal to 0. This is t and this is can be voltage or current. Okay. So how do you represent in the circuit form that the signal is starting from t is equal to 0, right? This is t is equal to 0. So this you represent with a switch. For example, if you have a DC source like this and here you have a switch. Okay. So step input means the switch is being closed at t is equal to 0. Okay. So this you can write as, if this is Vs, then this you can represent as Vs u of t. The minute you write u of t here, it means that there is a switch which is being closed at t is equal to 0. Okay. So this can be represented in this manner. Now what if the switch is closed at a different instant of time? That means you have Vs and the switch is being closed at some t is equal to t naught time. Then what will you do? You will just write a time shifted step response. Okay. So Vs u of t minus t naught. T minus t naught means the signal will be shifted by t naught to the right side. Okay. So that means if you represent in the form of a graph, if this is t naught, this is going to start from here. Okay. So this is the time shifted step response. And if the magnitude is 1, see here, if the magnitude is 1, then it is unit step response, otherwise it is simply step response. Okay. So similarly you can do the same thing for a current source as well. There is a current source, let us say, and the switch is being closed at t is equal to 0 or t is equal to t naught, you can take that as well. So this you can represent as Is u of t. So for an RC or an RL circuit, the minute the switch is closed, then there is a change in the circuit condition. Okay. So there will be a transient part, there will be a transient response. That is what we are going to discuss. What is the response when a step input is given to an RC and an RL circuit? Okay. So first we will start with the RC circuit. Step response of RC circuit. So you can draw the circuit. You can either draw it with a switch like this. This voltage we can take as Vs. This is R and C. S means the subscript S you are using to indicate source. So this you can take as switch closing at 0. Okay. Otherwise you can represent as Vs u of t. Either way it is going to be the same thing. Now the minute the switch is closed, let us say a current I is flowing and this I will have a transient part. Okay. So this is the current I. Now initial values are important. Okay. For a capacitor we will need the initial voltage value across it. So we will take the, let capacitor or initial capacitor voltage be V naught. Initial capacitor voltage be V naught. Okay. So that means V of t is equal to, we can take this as Vc, Vc of t. Okay. So here Vc of t is equal to 0 minus, that means just before the switch is closed, just before switch closes, the voltage is given by V naught, let us say. Okay. Now we know that abrupt change in the capacitor voltage is not possible. So after the switch is closed, that means at the instant 0 plus, t is equal to 0 plus. Okay. So this means just after switch closes, this is also equal to V naught. This is the biggest funda in transients. You need to equate the capacitor voltage just before switch closes to just after the switch closes. They are both going to be same, okay, because the voltage across capacitor cannot change instantaneously. Now, after this information is known, we can apply the KVL, okay. So, this is the current flowing. So, now what will be the KVL? Applying KVL, we get Vs u of t is equal to IR plus Vc. Now, I, how we can write? We can write it as C times dV by dt. So, Vc u of t is equal to C dV by dt into R, this is Vc, plus Vc, because the same current that is passing through the capacitor is passing through the resistor as well. Now, if you can apply the Laplace transform here, then what is the Laplace transform of step response? It is Vs by S, and this is equal to Rc, you can take out common, S times Vc of S minus Vc at 0. 0 plus or 0 minus is going to be the same thing, because voltage will not change. Voltage across capacitor, it will not change abruptly, plus Vc of S, okay. So, now you must be understanding here why we changed I in the form of Vc and not Vc in terms of I, okay. So, we will need to get in the form of Vc of S because we have the initial value here. So, if you rearrange, then you are going to get the function V of S, you will get as Vs plus SRC V0 divided by, here instead of Vc of 0, I have simply taken V0 because that was the initial value that we took, right, divided by SCR into S plus 1 by RC, okay. So, now if you apply the partial fraction, then you are going to get Vs into 1 minus S minus 1 by S plus 1 by Rc. So, you can do the partial fraction. I am writing the result, final result, V0 by S plus 1 by Rc, okay. So, we got it in terms of a form where we can easily apply the inverse Laplace transform. So, now if you apply the inverse Laplace transform, then you are going to get V of t, Vc of t. So, here put Vc, okay, voltage across capacitor. So, this is equal to Vs into 1 minus e to the power minus t by Rc plus V0 e to the power minus t by Rc. This is the final output. Now, you can see some very important observations here are, this is the same response that we saw in the source free RC circuit, okay. So, that means this is the output due to initial condition. And what about the rest of the part? This part is the output due to input or due to the source, okay. So, now the output due to initial conditions, this is often called as the natural response, and this is called as the forced response, okay. So, if it is due to initial conditions, it is natural response. If it is due to the source, then it is a forced response. So, this is one way in which you can interpret the output, okay, forced response plus natural response. There is another way as well. So, what is that? You can see here that this is an exponentially decaying function. This is also an exponentially decaying function. So, when t tends to infinity, this and this term will vanish. What will be left out? Only Vs, okay. So, Vs will be the final output, steady state output of Vc of t. So, we can write as Vc of t is equal to Vs, which is the steady state output, plus V0 minus Vs e to the power minus t by Rc. This is another way in which you can write the output, okay. That is the same output only, but in different forms. Here we are getting, this is the steady state part, that means it will remain even after the transient part dies. This is the transient part, and this will die out with time. This output, if you plot, then you are going to get, this is the time axis and this is the voltage Vc of t. Okay. So initial value you can keep by get by substituting t is equal to 0 here. Okay. So if t is equal to 0, then this will become 1. So Vc of t is equal to Vs plus V naught minus Vs. So V naught will be the initial value. So it will start here and then it is going to rise exponentially. And where will it settle down? The final value, it is going to be Vs. Okay. So from here you can write Vc of 0 is the initial value, which is V naught, and what will be the final value? This is Vs. What will happen if the initial value V naught is 0? Then it will simply start from the origin. Okay. Now once you know the voltage across the capacitor, you can find out the voltage across resistor. You can find the current through the circuit as well. How will you find the current? I of t is equal to C dV by dt. So you just have to differentiate voltage. Okay. So C dVc by dt. So we will do this C d by dt of Vs plus V naught minus Vs e to the power minus t by Rc. So what you are going to get here? V naught C times V naught minus Vs divided by minus Rc e to the power minus t by Rc. So you can write here Vs minus V naught by R e to the power minus t by Rc. Now the voltage across the resistor will be simply R times I of t. Okay. So once you find out the capacitor voltage, you can find out everything else. Let us now see how to simplify this procedure. Okay. How to simplify the procedure of getting the step response. Okay. We don't want to keep applying the Laplace transform and then apply inverse Laplace transform and so on. Okay. So we will simplify, we will see how. Now whatever we have discussed here, it is a simple RC circuit. There is only one resistor and one capacitor. Okay. Sometimes the circuit will be more complicated. In that case, you will need a simpler procedure. Okay. So if you see the voltage, we saw that Vc of t is equal to Vs plus V naught minus Vs e to the power minus t by tau. Okay. Now what was the circuit? This was the circuit. Now this is Vs, R and C. So what was the final voltage across the capacitor? It was Vs. This result we got from the mathematical analysis. Okay. But if you remember, I told you that the capacitor will act like an open circuit to the DC values. Okay. So that is the steady state condition. If you remember, there I talked about steady state condition, right. So what did I write? At steady state, capacitor acts as open circuit to DC voltage, right. So now what is happening here? Once the transients die out, as soon as the switch closes, there will be transient, but after the transients die out, the final voltage will be obtained by considering this capacitor as open circuit. So that means if you can represent, this is the circuit condition at infinity. So Vc of infinity will be what? It will simply be equal to this voltage, right? Vs. In fact, if you remember the current value we have found out, what is the current value? Vs minus V naught by R e to the power minus t by Rc. This is an exponentially decaying function. At t tends to infinity, I will become 0 because the capacitor is actually acting like a open circuit. So this is a very important significant point. Why that is the case, you will understand. Okay. So for now, you can see that Vs is now the final value, V naught is the initial value, and Vs is the again final value of the voltage, capacitor voltage. So now you can write Vc of t as Vc of infinity, the final value, plus Vc of 0, initial value, minus the final value e to the power minus t by tau. So that means whenever an RC circuit is given, if you can find out the final value, initial value and the time constant, if these three you have, then you can directly write the capacitor voltage using this expression. This is a very important expression. It's not just for this circuit, but for any RC circuit, this relationship is going to hold. But remember, this is only for a step response. When a step input is given, only then this equation is valid. Okay. So now the question comes, how to find the final value, initial value and time constant in a simpler manner. So this we will do by means of an example. That is when it will be more clear to you. Okay. And one more important point here is, just as an extension for this formula here, if switch is closed at t is equal to t naught, then you will have to write Vc of t is equal to Vc of infinity will remain same. Now the initial value will now be at t naught, okay, because the switch is closed at t naught, minus the final value e to the power minus t naught divided by tau. Okay. So this will be the only difference if the switch is closed at some other time other than 0. Here find V of t for t greater than 0 when switch is changed from A to B. Switch has been at A for a long time, okay, and this is the circuit. Now this might seem like a complicated circuit, especially given that you have just learnt the RC circuit. It is actually easy, okay. So that is what we are trying to prove here. The transients is actually very simple once you know how to do it in a better, simpler manner, okay. So what is the first step here? Step 1, just write the generalized expression for the capacitor voltage. V of t, we know this is the final value. See, here we will take as V only, okay, because it is given V of t, not Vc of t, plus the initial value minus final value into e to the power minus t by tau. Now what is the next step? You have to find each of the values. What are the three values you need to find out? You need to find out the initial value, the final value and the time constant, okay. So we will find them one by one. First we will start with the initial value, finding V of 0. Now how to find the initial value? You need the circuit at t is equal to 0 minus, that means just before switch is changed, just before switch position is changed, okay. So initially it was at position A, okay. So this capacitor was connected with this circuit. So what will be the circuit here? This is going to be 24 volt, and here you have 3 kilo ohm, 5 kilo ohm, and here you have the capacitor, okay. Now it is given that the switch has been in this position for a very long time. This actually means that steady state has been achieved before the switch is changed from A to B, okay. So when steady state is achieved, how will the capacitor behave? It will behave like an open circuit, okay. So at steady state you have Vc of t is equal to 0 minus. Now what will this be? This will simply be the voltage across this 5 kilo ohm, okay. So you can find that by voltage division, right? We got a very simple circuit, just a voltage division we got it, right? So it has been reduced to a voltage division problem. So Vc of t is equal to 0 minus is equal to 24 into 5 divided by 5 plus 3, which is 15 volt, okay. Then what will happen? Vc of this implies that Vc of t is equal to 0 should also be equal to t is equal to 0 minus this will be equal to 15 volt. Okay. Next, we found out the initial value. Next step is to find out the final value. Okay, finding the final value V infinity. Okay, so here once again, so just it will be a confusion, right? That's why just don't write this Vc, because since in the question only V of t is given. Now how will you find the infinite value here? This you have to draw the circuit at t is equal to infinity. Okay, so this is circuit at t is equal to 0 minus. Now we need to draw the circuit at t is equal to infinity. Okay, so we have the capacitor here, and this is position B now, resistor and a 30 volt DC source. And this value is given as 4 kilo ohm. Okay, so at t is equal to infinity means steady state. At steady state, what will happen to capacitor? It will act like a open circuit. Now what is the voltage appearing here? V of infinity, so simply 30 volt. Okay, so therefore we found out the final value as well. What is the next step? Next step is the time constant tau. Now here should we take the circuit at t is equal to 0 minus, that means before the switch is closed, otherwise after the switch is closed. Okay, so remember that since we are finding the expression for voltage after the switch is closed, after the switch is changed to position B, we will be needing this circuit. Okay, so what will be the time constant here? Whenever you have to find the time constant, you will have to look through the terminals of the capacitor. Okay, and you have to turn off all the independent sources. So what will be the Thevenin's equivalent? Looking through the capacitor terminals. Basically that is the equivalent resistance that you will need. So here anyways there is only one resistor, you don't have to worry much. When a more difficult problem comes, then I will explain more clearly to you. So here R is 4 kilo ohms and C is given as 0.5 millifarad. So the time constant we can find as R into C, which is 4 times 10 cube into 0.5 into 10 to the power minus 3. So this is 2 seconds. Now using all these values, you can finally write the expression for voltage. So what is the expression here? V of t is equal to the final value, which is 30, plus initial value, which is 15, minus final value e to the power minus t by 2. Okay, so that means you're going to get V of t is equal to 30 minus 15 e to the power minus 0.5 t. This is the expression for t greater than 0. Remember to write this, because t less than 0 there is a different expression. Okay, so this is only for t greater than 0 after the switch position is changed. Let us now see the step response of RL circuit. Okay, so what will be the circuit? You will have a voltage source, and here you have a switch, resistor and inductor in series. Okay, so here we can take this as Vs, and the switch we can take it to be closing at t is equal to 0. Otherwise you can simply write here Vs u of t. Okay, so I will draw it separately, or Vs u of t. Okay, this is R and L, R and L. Now let us take the current flowing to be I, so that we can apply the KVL. So applying KVL, you are going to get Vs u of t is equal to IR plus voltage across inductor you can write as L di by dt. Okay, but what is the polarity of voltage? Polarity should be like this. Okay, positive here, current should flow into the positive terminal. Then V of t is equal to plus L di by dt. Okay. Now when dealing with the capacitor circuit, we wanted the initial voltage across capacitor. Here what we want? We want the initial current across through the inductor. So you can write let initial current through inductor be I naught. Okay. So that means this is equal to I of t is equal to 0 minus just before the switch is closed, and it is also equal to I is equal to t is equal to 0 plus just after the switch is closed. Now here if you apply the Laplace transform, what you are going to get, Vs by S is equal to R times I of S plus L into S I of S minus the initial value of current, which is I naught. Okay. So from here you are going to get I of S is equal to Vs by S plus L I naught divided by R plus SL. If you apply the partial fraction, then you are going to get the final value I am writing, Vs by Sr plus I naught by S plus R by L minus Vs by R into S plus R by L. Okay. So now if you apply the inverse Laplace transform, then you are going to get I of t is equal to Vs by R plus I naught e to the power minus RT by L minus Vs by R e to the power minus RT by L. Okay. So now can you divide this in terms of the steady state response and transient response? That is one way of writing it. First we will write that I of t is equal to Vs by R is the steady state value plus I naught minus Vs by R e to the power minus RT by L. This is the transient value, right? So steady state value and this is the transient value because it is an exponentially decaying part. What is the other way of writing it? First one is, if you remember, I naught e to the power minus RT by L. This was the source free RL circuit response, initial value of current into the decaying part, right? So this we can take out and the rest of the part is Vs by R into 1 minus e to the power minus RT by L. So this is one way of writing it. The first part is the natural response, that is the output due to initial conditions. And the second part is the forced response. That is the output due to input. Now if you draw the characteristic response. So this is time, I of t as a function of time we want to draw. Okay. So what will be the initial value? If you substitute t is equal to 0, this term will become 1. So you are going to be left out with Vs by R plus I naught minus Vs by R, which is I naught. So it will start from I naught, which is the initial value, right? The current will be I naught right after the switch is closed. After that it is going to exponentially rise and it is going to settle down at some final value. What is that final value? You can substitute t is equal to infinity, which will make this term 0. So you will be left out with Vs by R. That is the steady state value. That's why we call it as a steady state value, right? So this is Vs by R. Okay. Once we know the current, then we can find the voltage as well. V is equal to L di by dt. Okay. Once you know this, then you can find the voltage across resistor as well using the KVL. Okay. So now we will write a generalized expression just like we did for the RC circuit. What is the generalized expression? In terms of the initial and final values. So I of t is equal to I at infinity, the final value, plus I of 0 minus I of infinity, the initial value minus the final value, into e to the power minus t by tau. Okay. So this is for the case of switch closing at t is equal to 0. Switch closed at t is equal to 0. Then what about if the switch is closed at t is equal to t naught. In that case, it will be I of infinity plus I of t naught minus I of infinity e to the power here again minus t naught divided by tau. Okay. So, this is when switch is closed at t is equal to t naught. Now, from all of this, the main takeaway point that you need to know is just after the switch is closed, how will the inductor and capacitor behave, and just after the steady state is achieved, how will the inductor and capacitor behave. These two if you know, then transients is very simple. Okay. So, what will happen to the capacitor? This is the capacitor and the initial value is V naught. Okay. So, you can write here, this is the initial value. Okay. So, that means this is the voltage just before the switch is closed. Okay. So, now how will this behave? Right after the switch is closed, it will behave like a voltage source. Right after the switch is closed. Okay. Remember that point, it is very important. So, it will behave like a voltage source which is giving a voltage V naught. Now, what if there is no initial value? Okay. Then it will behave like a short circuit. This is when V naught is equal to 0. That means no initial voltage just before switch is closed. Okay. So, this is the case of capacitor. Then what about inductor? Let us say the initial value of current is I naught. This is the initial current just before switch is closed. Then it will behave like a current source. And what will be the direction? Direction will be the same direction that is given here. Okay. And the magnitude will be I naught. Now, if there is no initial value, then it will behave like an open circuit. Here it is behaving like a short circuit and here it is behaving like an open circuit. Okay. So, if I naught is equal to 0, that is no initial current. So, this is just after the switch is closed. One more thing that we need to know is what? At steady state, how they are going to behave. At steady state, what is the behavior? First, if you consider the capacitor, it will act like an open circuit. Okay. And what about inductor? This will behave like a short circuit. Remember, this is only when the excitation is DC. That means the source that we are connecting is a DC source. So, just before the switch was closed, the capacitor was acting like a short circuit if there was no voltage. But at steady state, it will act like an open circuit, right? And for the inductor, just after switch is closed, it will act like a open circuit, but at steady state, it will act like a short circuit. Okay. So, these two if you can remember, then you can solve any problem in transients.